Now that we've had an initial overview of our Roland CNC, let's go ahead and jump into the softwares and take a look at how we would load some models and begin cutting them. If you recall, the software that is actually used to bring the model in and prepare it for the hardware is what's called the SRP Player. And what we get is this dashed line indicating the x-axis. And so what that's going to be is basically where we would put our blank on the x-axis here. And from there we would load a model and orient it and make it the correct size so that we can actually do some cutting on it. Now, for the sake of these tutorials, I'm going to actually do two different models, a rectangular as well as a cylindrical one. Jumping back into the machine, if you remember, with this fourth axis in particular, which I'm really going to focus on in these tutorials, one could take a rectangular piece and cut the top, and then the A-axis would rotate it, and then essentially cut it or mill it from the bottom, giving us an example like we saw with David, cutting from the top and cutting from the bottom and not the two sides. The second tutorial will then be using a cylindrical piece. So with this first rectangular piece, I just went out and cut a 2x4 chunk, and I like to put the dimensions on there so that we can keep these in mind and have them readily available while we're working through the SRP player. So this is a 10.5 inch slab, and as you know, a 2x4 is actually 3.5 by 1.5 inches. This is the 3.5, and then the Z is the 1.5. I do like to indicate the midline, and then kind of the point at which we're going to drive it into this peg. This is kind of the grounding peg that we would slide our blank into. So coming back into the SRP player, we're going to go ahead and open, and this does take the STL file as we had confirmed. I've already gone ahead and loaded a model for the sake of time. As we go through this computation, you'll see it can be a bit of a time-consuming process with a lot of variables that we might wiggle or play with. So just for the sake of this one, I've already loaded this, and then I'm going to talk through the logic that I used. So the actual model that we brought in is this blue, it's actually a jewel container. You drop jewels in there. This is the top and this is the bottom. This was generated in SolidWorks as a single part, and then it's a little bit hard to tell, but there's actually a support in between the two that then was complemented by the supports in this system. So it's actually a jewel box. A name has been put on there, a design, and the cavities have been put on the top, and this is actually the top of the jewel box, the bottom of the jewel box. So you see that there's a little bit of a logic here. And so essentially two pieces can be cut in this single project. So that's kind of cool. I wanted to show you that capability. When this is brought in, the information it's asking for is we need to confirm the size of the model. And so looking at this blank, remembering that we're working off these dimensions. So this blank is a 10.5 by 3.5 by the 1.5 here in the Z. And so we have to make sure that our model is going to fit within those parameters. So what I did is I put it at a X of not quite 5.6, a 2.6 of the Y, and then 1.378. So these were actually all kept in ratio. I can turn this off and manipulate. Let's say I wanted to make it a deeper pocket, or make it more oval. I could uncheck this ratio and play with these, but because I do want the symmetry so that the top and bottom will pop on and off, the depth is good. It's for rings and earrings, so it's not a real enormous part that we need. We're going to keep these. We could even scale it if need be, but we're going to keep it as is. If this came in at an orientation that is not this X orientation, we could manipulate it by touching one of these radio buttons, and it would flip our part. So if, let's say, it came in upside down or vertical and we wanted it horizontal, we could work with these buttons. I'm not going to do that because once you select one and it actually goes out of bounds, let's say it flipped upright and it's too big, we'd have to reset all the settings. So I'm just going to leave it as is. I also could then rotate it manually by degrees down here. The nice thing about this software is you see that this whole process is very linear. So the first number 1 tab is confirming the model size and orientation. So we've done that here. Let's go down into number 2. And this is type of milling. Select the type of milling that we want. Well, we would always think that we would want a better surface finish. If you notice, better surface is more curvature, smoother, more like a fillet, whereas faster time cutting is more like a chamfer, more angular. But the consideration here is when you run an analysis, you're going to see that the better surface finish is incredibly time consuming. And I'm going to show you what that means when we go into the actual analysis. So for the sake of most cuts, I keep it faster cutting time, and it's not really that much difference. What does matter is this second option, model with many flat planes or with many curved surfaces. So it's similar. You see that there's that flat plane. So let's say we had kind of a, let's say a mechanical part that was all right angles. That would probably be the appropriate choice for it. But here we have a lot of curvature in our model, some smooth organic pieces, curvature fillet here. So we're going to go with that option. Now, here we need to actually confirm whether or not we would need supports, and then also what type of workpiece we're going to have. We confirm that this is rectangular. It's not the cylindrical one, right? And we do want to cut it on the top and the bottom. We could just cut top only. Now we also need to add supports, and you know, you might be tempted not to add supports, but if we look at this, the problem is if we didn't add these pink bars here, once the mill cut through, our parts would essentially be suspended in space and thus would fall. And so we do need some kind of support that holds them. There's actually going to be a bit of the blank on both sides of this. So this cross beam will be a support, and then these two will be supports. And the way we're going to manipulate those or work on those is we're going to edit the model supports. And in doing so, we can come in here and we can basically push-pull these. They're a little touchy. Here we go. So I could move these all the way back, just because if we ran them, let's say, to here, they would interfere with the cavities of our tool chest, or our actual part. So we don't want that. So I'm going to move it back to just where it's supporting the outer wall of the piece. And obviously also here, if we were to, let's say, take one of these, and if we were to push these back, we may not have adequate support to, sorry, it's a little touchy. Even though there is this support that we built in using the SolidWorks model, the vibration and the pressure or the torque from the bit may snap this part. So we actually do want these supports in here. So we're going to slide them back And all four of these supports are separate. They'll go anywhere to basically to the origin, or all the way back where you can completely remove them. And then the other thing is, then we can also specify how thick we want them in terms of their width and their height. Anywhere below about 0.3, if you're using a 1/4 inch bit, is probably going to start being risky. If they're too small of supports, obviously they're not really going to hold. They'll probably snap or break. At the same time, if they're too thick, they might interfere with kind of the overall outcome of your model looking good. Now this will show us this perspective, how these are looking. So here it is on the top. You see that they're right at a good level. Like particularly this one is on the cup, the lower ridge level. If it were up higher, it might be a little bit more difficult to get the top to fit on the lower groove here. So you can move these up and down, and I moved it just below where that upper part of the cup is. And then obviously we could do the back. Here's the back view, and here's the right view. And so again, we could manipulate these supports from any of these, and here's the left view. Okay. Because I don't want to apply any of those changes because they already existed. I had already created them, so I'm just going to close that and stick with this model. So there's the supports as we created them. So now let's go ahead and go into step 3, create our toolpath. So here, what we are doing is we're going to have to provide a few pieces of information. First of all, the workpiece material. What type of material is it? And here is all of our options. This 2x4, we probably could have gone with the soft wood. Seeing as this is pine, it is rather soft. Hardwood is a better choice in my opinion because it doesn't take that much longer. It does slow down the RPMs, and it ensures that we have a firmer cut taking place. So we're not jeopardizing overheating of the head or too low of RPMs on the cut. So we're going to keep that hardwood. One thing on there, if you are using, we use a lot of foam. We have some foam here. That actually is this chemical wood. So just an FYI there. But you see the other options that we talked about in the overview. So here is where we'd actually provide the size of our blank at 10.5 by 3.5 by 1.5. This is the minimum parameters that our blank has to be. So if let's say our blank was less than 1.3781, the cutter would not allow us to use that blank. We'd have to go back in, or we'd have to reduce the size of our model. So this is just kind of telling us this is the minimum, this is what we actually have. And once we're done, we're gonna go ahead and create a tool path. Now, in doing so, we're gonna have to go ahead and get into our cutting options and decide what tool sizes and what type of passes we want. So we want roughing passes and we want finishing passes. In order to cut both the rough material, we want to cut all this excess material away quickly, and that would be done with the roughing passes. And then we would want the finishing to get more detailed. So in order to get the roughing on both the top and the bottom, we would need 2 roughing passes. So this one's going to be for the top and this one's going to be for the bottom. The finishing is where we would do a much slower cut, providing a much more kind of organic or circular cutting line. And so again, top and bottom, these we could move or orient differently, change the process by moving it up or down. If we decided we didn't want one, we could delete it. If we wanted to add one, so these, if we jump into them specifically, again, here is the top surface, and it's using a 1/4 inch ball. Starting to use that ball instead of a rounded, a squared off tip, because we want some of those rounder shapes, those fillets and whatnot. And then the finishing, we would use the 1/4 inch ball to start getting it much cleaner too. So these are both for the top, and then these bottom two are for the bottom. Now, in addition to this, we may want to add another pass, so a new process, and here is a new process where we would say, the 1/4 inch finishing is not going to give us the degree of detail that we want, so we need to go into finishing and create another finishing pass and utilize a tool change. And we could drop down to a much smaller one like the 32nd or even the 64th, but we may want to go incrementally down using, let's say, the 1/16 of an inch ball, let's say. And we could do that for both the top and the bottom. Again, for the sake of this tutorial, I'm not going to make these additional passes. And we would then, once we have completed adding and subtracting and working on all of our passes, we would actually go ahead and apply it, and we would create the tool path. It would then compute, it would essentially take that STL and the blank that we've provided, the information that we've given it, and it would generate a G code. And that would be essentially the code that would go to the machine. Once that's done, we can then go to step 4, and we can preview the results. Now, we do see that there is an estimated cutting time of 6.7 hours. If you remember back here in this prior step, I mentioned in this type of milling step, here, better surface finish, when I did that and estimated it, it bumped it up to 52 hours. So you see that there is some really, really significant time difference with just some subtle option changes. So again, we may need to do some playing and some testing to see what's going to work. Now, having our part here, we can now do a preview of this cutting. So I'm going to move this window out of the way. Here's our blank, and if you notice, it's starting the roughing cut, and then here comes the finishing cut of part 1, and now it's going to flip it and do the roughing part 2. It actually didn't visually show the flip, and then the finishing of part 2. So here, once it's completed, here is what it looks like. We can get a sense of how much is being cut away using a 1/4 inch bit for both the roughing and the finishing. Now, if you notice, like, the verbiage on this part just barely got scored, and some of the intricacy of the filigree or the patterning didn't really get cut. So we would most likely want to also put in a finishing cut using a smaller bit that would require a tool change, and we'll cover that when we actually go back into the machine. But the manual tool change then would provide much more detail, and we would be left with a beautiful finished product. So if this is something that we like, we've done this preview, then we would go into perform cutting. And right now it's telling us the only tool that we're using is a 1/4 inch ball, and it has to be at least 0.88 inches exposed from the collet in order to get into our blank. And I'll show us what that means as we get ready to cut this. But in other words, the depth of this is 1.5. We have to have 0.88 of the tool exposed, or else, let's say we only had 0.25 of it exposed, it actually would plunge the collet into our base, and obviously we would create quite a mess, and the part would not be cut. So we could start the cutting, or we could just send this to a file to save. Now, in order to start the cutting, we actually need to get our blank. So coming back to our blank, we need to get our blank on the machine and get the origin aligned and the bit in there, and then, and only then, would we start the cutting. So I just wanted to show you this, the SRP player and the steps that are required to prepare a file and then get our blank onto the machine to start it cutting. Next, we're going to take a look at creating a cylindrical model in the SRP player.